You'll be getting a new assignment tomorrow, due next week. I don't know how much reasonable content we've covered since then, so I guess we have what? Some Turing machine stuff, even though there's quite a bit of that in the current assignment.
I think the next homework will be the last homework, because we still have to do the project.
Good question. So the project and homework will probably happen simultaneously because I do want to have some assignment over limits of algorithmic computation over compilers. Once we're gonna start getting into that in the next couple of days. We're basically at the end of everything before the overview of compilers. So
We have a test next week too.
we do have a test next week as well. There's a
Like,
lot.
I feel like there's not enough time to finish the project and do two homework.
That is true. I don't even know what the project is gonna be yet. That's part of the problem with designing this course for the first time is I haven't really known what the schedule was going to look like. It's just when we get to things is when we get to things. And the project is going to be related to compilers, so I have to go over the material. Design the project and then give you time to do it. I don't know how to get all the learning outcomes done if we don't parallelize and have some project opportunity. Note that there is a project. If you're concerned about the project, implement the CYK algorithm and then you don't have to worry about the project. If you are banking on not having to do that and working on the second project, then you're possibly pigeonholing yourself into a lot of work at the end of the quarter. I don't know exactly what people's schedules look like, but yeah, we're coming down the home stretch here. I'll see what I can do. I will have a study guide to you all by Friday, though. Other questions before we get started? All right, so last time we talked about the difference between recursive and recursively enumerable languages. So we started with this class of language where we could find a Turing machine that accepts every string that is in the language in a finite amount of time, but said nothing about what happens when we reject. It could reject in a finite amount of time. It could go into an infinite loop and never finish. So that is a recursively enumerable language. A recursive language is one where we can build a Turing machine that can answer the membership question, can answer whether it's accepted in finite time or rejected in finite time. We found that recursive languages were a subset of recursively enumerable languages, and that was not true in reverse. There were some languages that were recursively enumerable that weren't recursive. We talked about how to enumerate these two different kinds of languages. Recursive languages are a little bit easier because we can answer the membership question. So all we have to do is construct a couple of Turing machines, one of which generates every possible string that could either be in the language or not in the language, everything that could reasonably be constructed with the alphabet. So we have one Turing machine just generating. If the language was ABC, it would generate the empty string A, B, C, AA, AB, AC, etc. Generate every possible string and then feed it into another Turing machine that answers the membership question. It says, yes, this string is in the language, or no, this string is not in the language. And running those Turing machines an infinite amount of time would allow us to eventually be able to enumerate the infinite language. We would always be producing new strings in the language. And for any string that you tell me, we could tell you how long it would take for this combination of Turing machines to generate and accept that string. So there is no string that is in the language that this combination of Turing machines would not eventually generate. That was a little bit easier to understand. And then we had this fun diagram where if we wanted to enumerate recursively enumerable languages, it got significantly trickier because possibly answering no, a string is not in the language, might put our Turing machine into an infinite loop. So we can't wait for it to terminate in order to make a decision about, is the string in the language, yes or no? So we needed to do this kind of diagonal iteration where we take every possible string that could be in the language, yes or no. So these are this W1, W2, W3, etc., are the same strings that were generated by the generator Turing machine in the recursive language. So if this was again the alphabet ABC, it would generate W sub 1 would be the empty string. W sub 2 would be A. W sub 3 would be B, C, AA, AB, AC, BA, etc. So we would have an infinite list of this, and then we would start to iterate down this diagonal path where we apply up to the first move, or up to the second move, or up to the third move of simulating this in the Turing machine. So we would have that many transitions at that period of time. So you'd see that the first string, we're just going to simulate the first move on, and then we're going to come back later and simulate the first two moves on it, and come back later and simulate the first three moves. The idea is if it terminates in a finite amount of time, then it will terminate eventually. If it does not terminate and goes into an infinite loop, then we will still be able to move on from it and consider other strings while still coming back and checking whether it terminates after more or more moves. Does that make sense? Let's see if I can find let's say I wanted to get the full history of every person in this class, and I would walk around to each of you and say something like, describe your entire life story. And I would sit there and listen to you as you described everything from the moment of your birth until right now. That would work only as long as each of you lived finite lives. Imagine that there's this wonder student sitting somewhere in the middle of the classroom where they've lived forever. If I go ask them to relay their entire life story, it's never going to end. And the students that I haven't gotten to and asked them about their life stories, I'm never going to learn about their life stories because this person who's lived forever is never going to finish talking. That's kind of a silly way to phrase it, but instead, what if I went around to the entire class and I said, describe yesterday? And then I went around to the entire class and I said, describe 2 days ago. And then the entire class and said, describe 3 days ago. The entire class described 4 days ago. That would actually get everybody's life story, even if there was somebody sitting in the middle of the room who has lived forever. It's very similar with this, except I'm going to ask the first student about the first day, the second student about the first day, the first student about the second day, the second student, the first student about the third day. And you just continue to diagonalize that until you eventually reach the one student left who is still spinning, and you can continue to query them. But in this, there are an infinite number of students in addition to an infinite number of days. So to be able to make sure that every student's history is eventually recorded, you need to use this procedure. We then talked about languages that aren't recursively enumerable and found that there are some of those. Real numbers between a lower bound and an upper bound was an example. The power set of an infinitely countable set was also not countable. And we used this theoretical concept to show that there are more languages possible than there are possible Turing machines that could exist. There are more languages, even though both are infinite, one is a larger infinite. You can map one onto the other and find that there are still some left over, even though they're both infinite. that actually maps to a really strange math problem where if I were to query people and ask, are there more positive integers or integers? What would you say?
Integers.
It's false. They're the same number. They're equally infinite, which means you can immediately map one onto the other. And for every element of the second set, there's an element of the first set that maps to it. There's no number you could give me in the set of integers that wouldn't have an associated positive integer for it. And because of that, those infinities are defined to be the same size. On the other hand, if you were to look at the integers versus the rational numbers, you would find that you in fact need additional integers to be able to represent unique rational numbers. So those actually differ in their size. So we can talk about things like the various sizes of infinities because of how they map onto each other. So because of this, we can map Turing machines onto languages and find that we can't have a Turing machine that defines every language. There are more languages than there are Turing machines. Again, I won't go into the details of exactly how that is done. That would probably be for a graduate level class. But I think this is where we stopped. Did we talk about complements? Yes, we did. We talked about this slide. This is the last thing we talked about. So we said if a language is recursively enumerable, its complement does not have to be recursively enumerable. There is a proof by contradiction in the book if you're curious, but what's important is just the outcome of whether or not a recursively enumerable language's complement is recursively enumerable, which it's not guaranteed to be. We also wanted to have an example for a recursively enumerable language that is not recursive, and of course those exist as well. This is going to be one of the tougher few slides, I think, of the class. I'm not going to ask people to do anything like this, but we're going to start talking about some ways of thinking about Turing machines and working with them to try to create some outcomes. We'll start by describing what we're going to call the universal language. The universal language is going to be a set of encoded pairs. We have a Turing machine that we're going to call M, and we're going to have a string that we call W. And this language is the result of running M on W. So for every possible Turing machine, for every possible string, the pair MW is the result of running machine M on string W. We call this the universal language because you can think of every Turing machine as any program that you could write in any language. Think of all existing Java programs, all existing Python programs, every possible program. There are an infinite number of them, but you can also think of any possible string W. What happens when you give algorithm M input W? What happens? So the universal language is what's defined to be the result of all of those computations. Questions about that? That's starting to think very big. It shows you the limits of what we can compute. Any algorithm can take any string as an input, or any input. If it doesn't take a string, it can be represented as a string. The goal is for us to be able to show that the universal language is recursively enumerable. Because we could define this as a language, right? Just like we can define any language we talked about this quarter as a language. You define the language of Turing machine string pairs as a language. How in the world could we show that it's recursively enumerable? Let's go over that. This, I'll just put this out there now. This is not something that I expect people to be able to replicate or even necessarily regurgitate. This is more so for the general curiosity of talking about it. There will not be problems related to this topic. But it shows you how this kind of reasoning is done, so that if you see it, you're able to understand it. That's the goal. All right. So to show that it's recursively enumerable, we're going to construct a Turing machine that's going to recognize the language. That's how we do anything, right? We want to show that something is something, we construct something that does that. So how do we do that? For ease of understanding, we're going to say that this Turing machine that represents the universal language is going to be a multi-tape Turing machine. So multiple tapes. The first tape will have the encoding of the Turing machine M and the string, separated by some separator character. So we would have some way of reading through and saying this is the string representation of a Turing machine, followed by a symbol that says we're done with the definition of a Turing machine, followed by the string that is going to be run on that Turing machine. So all of the input to the universal language. It's the tuple machine string. So that's step one. Step two, with a second tape, we're going to simulate running machine M on string W. Because we know we have that string representation of the Turing machine, we can understand exactly what it's going to do. Think of it like you doing a code review on somebody else's code. You are probably in your head simulating what their code does in your head, reading their instructions and running it in your head and producing output and seeing if that output matches what you expect for them to have provided in that code review, in their code. So as we do this simulation, the output from the simulation is going to be applied to tape 2. We have a third tape. The third tape is needed to keep track of M's current state. All of the rules of what states exist and what the transition rules are applied on the first tape. But the third tape needs to keep track of what is the current state as we apply M to W. So that will need to be represented on some tape. And then you can just assume that there's a fourth tape that's used as kind of scratch paper or scratch work of something that's keeping track of an internal state. And this is what guarantees that we have an infinite amount of memory and it's parallelized so you know exactly which tape to look at. Now we need to describe exactly how this process is done. So we're going to simulate M. The Turing machine that we're constructing, this 4-tape Turing machine, will use tape 1 to define the transitions of what happens when M. So current state of M, we're reading from tape 3 to figure that out. And the tape symbol of M, which is stored on tape 2. We then change the contents of tape 3 to record the new state as we go through the transition. So we'll identify on tape 1 which transition is appropriate. Based on where we are in tape 2, the simulation. which allows us to make modifications to tape 3, which is the current state of the machine. Any questions on any of this logic so far? Exactly how we're simulating this or what we're doing? So this machine is going to change tape 3 to record a new state after a transition. It's going to change the tape symbol on tape 2. So we're moving forwards on the string. We move the tape head left or right on tape 2 as specified by the transition. Because tape 2 is giving us the current position in the string. And you can use this process to simulate this entire behavior. If eventually M enters a final state, signaling that it accepts W, then our Turing machine will accept this coded pair and halt. This shows us that the universal language, the language that's represented by this Turing machine, is one and the same. This machine will be able to recognize the universal language. So we've constructed a Turing machine that's capable of simulating another Turing machine's computation on a string. This is the general concept behind emulation of any kind. Whatever you happen to be emulating, you need to, with your tools, be able to construct an algorithm that simulates another tool. So this is exactly what a digital computer does, right? We specify an algorithm in some programming language, and the computer will simulate going through and doing those things on itself. So it simulates the instructions that are given to it. So this is what shows that a Turing machine is capable of doing everything that a modern computer is, because it can recognize any algorithm input pair. So cool. The universal language is recursively enumerable. What do we think? Is the universal language recursive? Will we be able to answer no and not just yes? Is there any way that you, this machine that we just created, could possibly get into an infinite loop if M does not accept W? Or goes into an infinite loop itself? Any thoughts on that? Yeah?
My intuition would be, yes, it can get into a loop, but I'm not quite sure how to phrase it.
Yeah, so assume that this thing that we're simulating goes into an infinite loop. In order for this to be recursive, we would need some way of recognizing that M on W is in an infinite loop. So the answer is no, it's not recursive. But the reason it's not recursive is we can't actually answer that question. We can't figure out if this, in the middle of this simulation of M on W, is it in an infinite loop, yes or no? And we'll actually come back to this as we talk about the halting problem. But we can show this as a proof by contradiction. So proof by contradiction makes the supposition that it is recursive. And then goes through some logic and arrives at a contradiction. So let's figure out what that contradiction is going to be. If it's recursive, then there exists a Turing machine that accepts the complement of it. This is the reason that I introduced the concept that the complement of a recursively enumerable language does not have to be recursively enumerable. So imagine the complement of the universal language. First of all, what does that even represent? Yeah,
I'd ask for the complement of LU.
yeah,
So would that be the language of nothing, basically?
it's the language where, yeah, so U is the language of every possible algorithm input pair. It's kind of tough to visualize, huh? But what about the set of real numbers? You can imagine passing some element of that. What happens? It's not really defined, but we would need some way of being able to accept or reject, to say something like, is this a member of this language? If we're not able to answer that question, then it's in the complement of the universal language. So things that aren't computable. So we would need to be able to construct a Turing machine of things that aren't computable. A Turing machine that would recognize things that aren't computable. So what we're going to do is we're going to transform our Turing machine M that accepts the universal language into another one that accepts a language that I'll describe really shortly, the diagonalization language. So we will transform the input string into a pair duplicating itself. So we have a tuple of the input string, the input string. This new Turing machine is going to assume that the first string in that tuple is the encoding of another Turing machine, and the second W is an encoding of a binary string. Since this Turing machine accepts the complement of the universal language, this machine M will the original machine M will accept the tuple WW if and only if M sub I does not accept W sub I, if that makes sense. So we're simulating M sub I on W sub I. And now we have a reversed acceptance because of this. If this machine exists, if this machine M exists, then it will accept only if simulating M sub I on W sub I rejects, and vice versa. So this ends up being in the diagonalization language. So this tells us that M prime accepts the diagonalization language. This is half the proof. The other half of the proof is we need to show that no Turing machine can recognize the diagonalization language. If that is the case, then we can conclude that the universal language is not recursive. So the proof of that will define the diagonalization language as we assume we have some infinite sequence of all binary strings, all of them, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. We will let an infinite sequence of Turing machines be the enumeration of all possible Turing machines. Since we said they have binary representations, then eventually we're going to produce some binary strings that happen to represent Turing machines. The diagonalization language says that to be in the diagonalization language, it needs to be one of these binary strings, W sub I, such that it's not a language, it's not in the language accepted by the ith Turing machine. Does that definition make sense? Take a second to look at that. So we produce our first W sub I, 0. M sub 1 is the first Turing machine in an enumeration of all Turing machines. We could simulate and pass 0, which we're calling W sub 1, to M sub 1, this first Turing machine that is generated. And we'd be able to answer whether or not that machine accepts W sub 1. If it does, then this string is not in the language of that machine. So if it is in the language, then it's not in the diagonalization language. If it's not in the language, then it is in the diagonalization language. So we want to show that this is not recursively enumerable. How do we do it? Suppose that we're able to construct some Turing machine for it. What happens when M sub I parses W sub I? If M sub I accepts W sub I, then by definition, it's not in the language, then not in the diagonalization language. If it does not accept the string, by definition, it is in the diagonalization language. What this tells us is W sub I can neither be in the diagonalization language or not in the diagonalization language. It's in neither, which is folly. When we have a binary, it's either in it or it is not in it. It can't not be in it and not be not in it. That doesn't make sense. So we've defined our contradiction that the diagonalization language is recursively enumerable. Going backwards through all of this, we can see that this completes our proof on the prior slide that M prime accepts W if and only if W is in the diagonalization language, but no Turing machine can possibly recognize the diagonalization language. Therefore, the universal language is not recursive. So the entire reason I wanted to go through this kind of a concept is just to show you what Turing machine related proofs look like. I will not ask you to do this on homework. I will not ask you to do this on an exam. This is just so that you get a sense of what does it look like to reason theoretically about Turing machines, which is an important outcome, I feel like. The entire reason we introduce these is so we can make high level or to get high level understanding of computer science as a whole, to figure out what is possible and what is not possible. This is not everybody's forte, areas of interest, but it is something that we can do to make sweeping generalizations about what is or is not possible, given the tools that we have. If the tool we have is the modern computer, then we can emulate any recursive language. We can produce algorithms for recursively enumerable languages as long as we're intelligent about what happens if they enter an infinite loop. And there exist languages that are outside of that scope completely. How do we reason about what languages fit where? Well, we need to come up with a theoretical argument that says whether or not it is possible. Because with our computers, we have a limited amount of RAM. We only live so long. There are some algorithms that are possible and finish. They just take longer than we have left to live. So we need to be able to make some kind of theoretical argument about whether or not it's theoretically possible to do this, even if practically it's not possible yet, or might never be practically possible to do. It's still an intriguing question to ask. is it possible given this kind of a tool, a digital computer? All right, next thing we actually care about. I made this hint, I think, at the very beginning of this lecture that I had introduced you to context-free grammars that had no restrictions. And then I said that is not technically true, and I would come back and explain why and how that is not technically true. So yes, I lied to you. Has anyone thought of the way that context-free grammars is restricted? Yeah,
You have to check out state, which state you're gonna go into. It'll let you go from S to A, you can't go from S to B like automatically.
okay, like via a lambda transition. You could if you defined A goes directly to B. Like S goes some way to A goes directly to B.
But you have like nothing that goes to B, B has different functions. That's restricted.
Okay, interesting. I can understand that. Not what I'm looking for, but it's an interesting idea. It's technically not limited on the right-hand side. What have we said about the left-hand side of a context-free grammar?
There's only one symbol.
Yes, there's only one non-terminal on the left-hand side. So unrestricted grammars are gross because we can now lift that restriction and says any number of terminals or non-terminals in any order can appear on both the left-hand side and the right-hand side. You have no restrictions on even how we define the rule. A rule had to be some variable is defined in terms of something. But now we can have anything map to anything. So now we can have one or more terminals on the left-hand side of a production. We can have more than one non-terminal on the left-hand side of a production. Any number of terminals or non-terminals.
Right.
There is one thing that would create nonsense, and that's that we can't have lambda on the left-hand side. We can't redefine lambda. So that means we have to have at least one terminal or non-terminal on the left-hand side. If we had to make a guess, what is the power of an unrestricted grammar? Let's first say more, same, or less powerful than context-free grammars. Guessing more? Who thinks the answer is more? Less? Equivalent? Interesting. How to split between more and equally? The answer is more. There are things that we can do with unrestricted grammars that we could not do with context-free grammars. We'll see what that is in a moment. More, same, or less powerful than recursive languages. Who thinks the answer is more powerful than recursive languages? Less powerful than recursive languages? Equally powerful to recursive languages? Good guess. It is more powerful than recursive languages. How about more, same, or less powerful than recursively enumerable languages? More powerful? Less powerful? Equally powerful? Hunter hasn't. we finally found the appropriate similarity between unrestricted grammars and the languages that they represent. So we can justify this somewhat, but it's interesting to note that context-free grammars map to non-deterministic push-down automata, map to kind of how we structure programming language syntax. But if you relax every possible constraint, you end up with this concept of recursively enumerable languages, of the ability to say yes, but not no. What does that tell us about an unrestricted grammar? Can we answer the membership question? Can we determine whether or not a string is in the language defined by an unrestricted grammar?
Not always.
Not always. Yeah, we can always answer yes, but we may not be able to answer no. Sometimes it may terminate and tell us no, and sometimes we may get stuck in a loop in the grammar and not be able to terminate the grammar. So what is the process of being able to go through and parse an unrestricted grammar? Start with the start non-terminal. We still have a start non-terminal. So the very first production is going to have a particular start non-terminal and be defined in terms of that start non-terminal. Where we go from there, who knows? You can start by saying, look at all strings that can be derived from the start state within a single step. So we say by applying one production rule, S arrow, we know that there could be any number of productions on the right-hand side. What could be done with a single step? All of the strings that can be generated with a single step. Enumerate all of those, write them all down. Since there are a finite number of productions, the list will be finite of what we can do in a single step. We'll never be able to generate an infinite number of strings within a single step. Next, we look at 2 steps ahead and say if we were allowed to go to one production and then take that production and go to another production. What are all of the strings that we could generate within 2 steps? Since there are a finite number of productions, that will be a finite number of strings. You continue this process for 3 steps, 4 steps, 5 steps, 6 steps, and this process will not terminate, but it will always be able to produce more and more and more strings in the language. For any string that's in the language, there exists a finite number of steps that we can walk through in the grammar that gets us to that point where we output that string. However, that is not guaranteed for strings that are not in the language. What's fun is we can map this process to a Turing machine. The alternate process is also possible. Take a Turing machine and devise an unrestricted grammar for that Turing machine, but that's extremely difficult. There's a big long proof in the book about how this is done. I'm not going to bother to go over it because it's not particularly relevant. So again, I give you this concept of an unrestricted grammar just so that you know what it is. I'm probably not giving you homework questions on it or putting it on an exam because even really simple unrestricted grammars are extremely difficult to come up with and have a ton of productions. If I give you a problem and say come up with an unrestricted grammar, it very well may have 12 productions or 15 productions, even if it's extremely simple. And it's just outside the realm of what I think is an important takeaway from the course. But it's good to know that they exist and what they map to. We can use this to come up with a slightly more interesting and more relevant kind of grammar called a context-sensitive grammar. We talked about context-free grammars that don't care about the context, but now a context-sensitive grammar is going to consider its context. So there are many different classes of grammars. Somewhere in between the power of a context-free grammar and the power of an unrestricted grammar, they mostly turn out to be uninteresting. They don't do anything new for us or provide us with any kind of tangible benefit that we are aware of in modern computer science. However, this context-sensitive class is studied a lot because it maps to this new concept that we'll talk about called a linear bounded automata. So the rules of a context-sensitive grammar, we still allow any number of terminals or non-terminals on both the left and right-hand sides. There is one important condition that we need to meet. The number of terminals and non-terminals on the left-hand side of each production have to be less than or equal to the number of terminals and non-terminals on the right-hand side. It's an interesting restriction that tells us that we have to define fewer symbols in terms of more symbols. Why do we think we care about that? Why is that interesting? I'll let that settle for a bit. We are out of time for the day. We'll come back at this point tomorrow and answer the question. Today was dense. Let me know if you have any questions about it or just kind of want to discuss it or talk about it, and I'd be happy to do so.
Yes, okay.